So I want you to visualize a very specific, totally terrifying scenario.
Oh, boy. I think I know where this is going.
You probably do. You're an MBA student, right?
Right.
And you are sitting in this massive, freezing cold lecture hall.
Yeah.
It's the final exam for your core corporate finance module. And the clock at the front of the room is just ticking down with that heavy mechanical clack.
The worst sound in the world.
It really is. And the silence in the room is deafening. Like, it's only punctuated by the furious scratching of pens and the frantic tapping of calculator buttons from everyone around you.
Panic tapping.
Exactly. So you turn the page of your exam booklet and your heart just absolutely sinks. Because staring back at you is this massive labyrinthine capital budgeting question.
With cash flows going every which way.
Right. Different interest rates for different periods, terms that seem literally designed to confuse you. It's like a minefield. And, if you don't have a foolproof mental framework to crack this problem, panic is going to set in.
And the exam just slips away from you. Yeah, it is a universally terrifying moment for business students.
Definitely.
Because unlike a simple accounting balance sheet where, everything neatly ties off to zero, valuation problems exist in the fog of the future.
Which is so abstract.
It is. You're basically being asked to diagnose the financial viability of a multi-million-dollar project that hasn't even happened yet, and the pressure is incredibly high.
So how do you survive that? Because just memorizing formulas doesn't work, right?
No, absolutely not. If you try to survive that moment by just regurgitating a memorized list of formulas, the slight variations in the exam wording will break you. You really need an intuitive understanding of the mechanics.
Which is exactly the mission of today's deep dive.
Yeah.
You're going to build this impenetrable armor of understanding around the foundational concepts of corporate finance valuation.
Specifically, the time value of money.
Or
TVM.
Yes, the TVM. And we're going to do it without turning this into an audio textbook. Because let's be real, you're balancing case studies, group projects, networking, and you just do not have time to listen to a dry list of algebraic variables.
Right. Nobody wants that.
So we're going to extract the underlying philosophy from our source material. We want to build a mental framework so sturdy that in that high-pressure exam, you won't be struggling to recall formulas. You'll just feel them in your bones.
I love that. And honestly, stripping away the academic jargon reveals one unavoidable truth. Money is a time traveler.
Ooh, a time traveler. I like that.
It is. Its value is fluid, warping depending on the exact moment it exists in time. So our goal today is to teach you how to drive that time machine.
Okay, let's pour the concrete foundation first, because before we even touch a calculator, we have to establish the philosophical why.
Because if you understand the theory, the math just becomes a natural extension of your logic.
Exactly. So the core premise introduced right at the start of our sources is this time preference for capital. Simply put, money in your hand today is measurably worth more than the exact same amount in the future.
Right. And examiners absolutely love to test you on the why behind that. They want to know if you can articulate the theory.
So for the listener mapping out their study strategy, I want to give you a memory hook right now. When you get your scratch paper in the exam, write down RICI.
RICI. Risk, inflation, consumption, investment.
Yes. The 4 pillars of time preference. Let's unpack these, starting with the R. Risk and uncertainty.
Well, the future is a fog, right? It's fundamentally unknowable. Think about a business. Outflows, like the checks you write, those are in your control. But future inflows, totally at the mercy of the universe.
100%.
You might have a signed contract for a payment in 12 months, but the counterparty could default. Or a massive macroeconomic event could wipe out the industry.
Like the classic bird in the hand principle. A rupee today is 100% certain. A rupee tomorrow is just a probability.
Exactly. And because of that inescapable uncertainty, a rational actor demands a premium for waiting.
Which leads us perfectly to the first I in RICI, inflation, the invisible thief of purchasing power.
Oh, it really is a thief. In an inflationary economy, the money you receive tomorrow simply buys fewer real-world goods than the money you hold today.
Right. The nominal value, like the number on the bill, is the same, but the functional utility is decaying.
You're losing wealth just by letting time pass.
Okay, let me throw a curveball at you, an exam trap, basically. What if inflation is 0? Or what if we have deflation and prices are dropping? Does the time value of money just, stop applying?
Oh, that is a classic trick question. The answer is an absolute no. TVM still applies.
Why?
Because RCI is a 4-pillar system. Even without inflation, you still have risk, like we just talked about, and you still have the last 2 pillars.
Right, so let's hit the C. consumption. This is basically just human impatience, isn't it?
Pretty much. It's innate. We prioritize immediate gratification over deferred utility. We just want things now.
So a company would rather have cash today to distribute to owners or satisfy current needs rather than waiting.
Exactly. Deferring capital forces a delay in gratification, so you have to be compensated for that delay.
Okay, that brings us to the final IB in RACI, investment opportunities. This feels like the most crucial one for an MBA.
It absolutely is. This is opportunity cost. If you have, say, 1,000 rupees today, you can put it in a bank at 8%.
Right.
And in a year, you have 1,080 rupees. So if you're forced to wait a year to get that initial 1,000, you don't just lose time.
You lose the 80 rupees you could have made.
Exactly. You forfeit the investment opportunity. So remember RSCI for the exam. Risk, inflation, consumption, investment. That's your theoretical foundation.
Okay, foundation poured. Now let's shift the time machine into drive. We're moving to the forward view, which is compounding or future value.
Right. How money grows over time.
But before we get into the math, what is the actual difference between simple interest and compound interest? I feel like people mix these up constantly.
They do. So simple interest is stagnant. It's calculated only on your original principal.
Just the starting amount.
Exactly. But compound interest, that is the engine of wealth creation. That is interest on your interest.
Okay, so exponential growth. Like a viral video. One person shares it with 2, they share it with 4, then 8. The base is constantly expanding.
That's a great analogy. The interest you earn is immediately put back to work to earn more interest.
Let's look at the formula for this. The magic future value equation. It's FVN equals PV times 1 plus R to the power of N.
Right. And let's carefully define those variables for the listener. FVN is your future value in year N. That's the destination.
And PV is the present value, right? Your starting cash.
Yes. R is your annual rate of interest, and N is the number of years.
Let's walk through an actual example from the text, example 4.2. Say you invest R's 1,000 at 10% for 3 years.
Okay, so let's break down the compounding year by year. Year 1, you start with 1,000. 10% interest is 100 rupees.
So you end year 1 with 1,100.
Right. Now, year 2, your base is 1,100. 10% of that is 110.
Oh, so the interest amount grew from 100 to 100.
Exactly. So end of year 2, you have 12,210. And in year 3, 10% of 12,210 is 121, giving you a final future value of 1,331 rupees.
The power of the exponent doing its thing. But doing that by hand for like 20 years would be a nightmare on an exam.
It would be terrible, which is why we have the future value interest factor tables, or FVIF tables, Exhibit 4.1 in your materials.
The tables are a lifesaver. You just find the intersection of your interest rate column and your period row, right?
Exactly. Let's use example 4.3. You have 50,000 rupees at 10% for 5 years. You don't calculate year by year. You go to the 10% column, down to the 5-year row, and you find the FVIF factor, which is 1.611.
So you just multiply 50,000 by 1.611.
Yep, and it instantly gives you 80,550 rupees.
So fast. But here's where it gets really interesting, and where examiners love to lay traps. Multiple compounding periods.
Oh, yes, the frequency trap.
Because in the real world, interest isn't just compounded annually. Banks love to do it semi-annually, quarterly, or even monthly.
Right. And when that frequency increases, the exponential growth accelerates because the interest is reinvested faster.
So how does that change the formula for the exam?
You have to adjust it. The formula becomes FVN equals PV times 1 plus R over M, all raised to the power of M times N.
Okay, wait, what is M?
M is the number of compounding periods per year. So let's look at example 4.4. You invest 2,000 rupees at 20% per annum, but it's compounded semi-annually for 3 years.
Semi-annually, so that's twice a year, meaning M is 2.
Exactly. So first, you divide the annual rate by M. 20% divided by 2 gives you a functional rate of 10% per period.
And then you multiply the years by M.
Yeah.
So 3 years times 2 periods a year is 6 total periods.
Right, so your R becomes 10% and your N becomes 6. You run that through the compounding engine and you end up with 5,187.50 rupees.
If you hadn't adjusted that, you would have gotten completely the wrong answer.
Yeah.
You have to watch out for the word compounded.
It is the easiest way to lose points on the exam.
Okay, so up to now, we've only been moving single lumps of cash, like one deposit of 2,000 rupees.
Yeah.
But real businesses deal with constant streams of cash.
Right. They don't just make one investment and walk away. We have to upgrade the time machine for multiple passengers.
Let's look at table 4.2. Future value of a series of payments. Say you deposit 1,000 rupees at the end of year 1, 2,000 at the end of year 2, 3,000 in year 3, and 4,000 in year 4, all at 5%.
This is an uneven stream. The key logic here is you cannot just add all those numbers up and compound the total. That violates the math.
Because the 1,000 rupee deposit sits in the account way longer than the 4,000 rupee deposit.
Exactly. You have to calculate the future value of each individual deposit based on its specific time in the account and then sum those final compounded amounts up.
Right. And in table 4.2, that gives you a total of 10,841 rupees. It's a bit tedious to calculate.
It is, which is why finance loves uniformity. Enter the annuity.
Ah, the annuity. This is a massive concept. What are the defining features here?
For a series to be an annuity, it must have equal payments occurring at evenly spaced intervals, like a lease or a monthly rent payment.
And there's a huge key term alert here for the listener. The difference between an ordinary annuity and an annuity due.
Yes, exam tip. Always check the wording of the question. An ordinary annuity means the payments happen at the end of the period.
Like paying a mortgage at the end of the month.
Right. An annuity due means payments happen at the beginning of the period, like paying rent on the first of the month.
That timing changes the math completely, right? Because an annuity due gets an extra full period of compounding.
Exactly. But let's focus on calculating the future value of an ordinary annuity, or FVOA. You use a different table for this.
The compounded interest factor of an annuity table.
Yes. Let's do example 4.5. You deposit 5,000 rupees at the end of each year for 5 years at 6%.
Okay, so it's 5,000 a year. Uniform payments. That's an ordinary annuity.
So you go to the table, find 6% for 5 years, and the factor is 5.637. You just multiply your 5,000 payment by 5.637.
Wait, so 5,000 times 5.637. That's 28,185 rupees.
Boom. Done. It's a massive shortcut compared to calculating 5 separate future values.
Seriously. Okay, so we've mastered pushing money forward. But in corporate finance, you usually know the future expected returns of a project, and you need to figure out what that's worth today.
Right. To decide if you should actually invest in it right now, this requires reversing the math.
The backward view. Discounting a present value or PV?
Present value is literally the exact opposite of future value. Because money can earn interest, the present value of a future sum is always going to be less than its future value.
So we just inverse the formula. TV equals FVN divided by 1 plus I to the power of N.
That's it. Instead of multiplying by the growth factor, you're dividing by it, stripping the phantom growth away.
Let's do example 4.6. You have the opportunity to receive 1,060 rupees 1 year from now, and the discount rate is 6%.
Okay, so you take the future value, 1,060, and divide it by 1.06 to the power of 1.
Which gives you exactly 1,000 rupees today.
Right. And example 4.7 is receiving 150,000 rupees in 5 years at 8.5%. Same logic, you just use the PV formula or the PV tables to shrink that 150,000 down to its worth today.
What's really fascinating here is the conceptual relationship between the discount rate and the value.
Oh, this is a frequent multiple choice target. It's an inverse relationship.
Right, like a seesaw.
Exactly. The higher the discount rate, say you have high inflation and high risk, the less valuable those future amounts are. They shrink drastically.
And the lower the discount rate, the more valuable they are today.
Yes. It's crucial to grasp that conceptually, not just mathematically.
Okay, so bringing it all together, just like we had a series of payments for future value, we have to apply present value to complex streams of income. This is capital budgeting.
The ultimate application, the so what of this entire chapter.
Let's look at the PV of a series of cash flows first. The summation formula. Example 4.8. You have a government bond yielding 10,000 rupees in year 1, 12,000 in year 2, and 11,000 in year 3. Discount rate is 10%.
So you use the present value interest factor table, table 4.3. You find the factor for year 1 at 10%, multiply it by 10,000. Find the factor for year 2, multiply by 12,000.
And you do that for each individual year, then sum them all up.
Right. And that gives you a total present value of 27,188 rupees.
So how does this actually apply to an executive making a decision? Let's bring up example 4.1. This is the big one.
Yes, the accept or reject decision. Let's lay it out.
A company is looking at a project. It costs an initial 1,000 rupee outflow right now at 0 year, but it's projected to bring in 20,000 rupees a year for the next 6 years.
Okay, so a naive manager would just say, well, 20,000 times 6 is 1,020,000. That's more than the $1,000 cost. Let's do it.
And they would be totally ignoring the time value of money.
Exactly. You cannot compare future inflows directly against present outflows. You have to find the present value of those 20,000 rupee inflows.
Drag them back to year 0.
Yes. And if the present value of those inflows is greater than or equal to the 1,000 rupee initial investment, the firm accepts the project.
But If the PV of the inflows is less than 1,000, they reject it, even if the nominal future cash looks higher.
Precisely. That is the ultimate practical application for an MBA. It's called net present value.
And since those 20,000 rupee inflows are a uniform series, we could use an annuity shortcut, right?
You can. The present value of an annuity formula, let's use example 4.9 to show that.
Okay, so you get 1,000 rupees paid at the end of each year for 5 years at 8%.
You go to the PVF table, table 4.4. 8% for 5 years gives you a factor of 3.993.
Multiply that by the 1,000 rupee payment, and you get a present value of 3,993 rupees. One simple step.
It saves so much time on the exam.
So we've looked at corporate projects, but let's shift to something everyday: loans.
Oh, yes, amortization.
Amortization schedules. This is the ultimate everyday application because it's just the PV of an annuity concept applied to debt.
Right. Amortization means paying off a borrowed sum completely over time, so the balance is exactly zero at the end.
These are equal periodic payments that include both principal and interest. Everyone knows them as EMIs.
Yeah.
Equated monthly installments.
Exactly. And the math is just the annuity formula worked backwards. The loan amount you get today is the present value.
And the EMI, the payment you have to figure out, is the annuity variable. Let's run example 4.0.
Okay, you borrow 50,000 rupees at 10% for 5 years.
So the 50,000 is our PV.
Right. And we need to solve for R, the annual payment. The formula is 50,000 equals R times the PV IFA factor for 10% over 5 years.
Looking at the table, that factor is 3.791.
So you take the 50,000 and divide it by 3.791.
Which gives you an annual payment of 13,189 rupees.
Every year you pay that exact amount, and it perfectly covers the interest and zeroes out the principal by the end of year 5.
Exam prep reminder for you listening. If you see a question about an auto loan, a consumer loan, or a mortgage, your brain should immediately flash the words amortization and PV of an annuity.
That will point you directly to the correct formula.
All right, let's recap this journey. We started with the philosophy, understanding why time is money, using the RICI pillars: risk, inflation, consumption, investment.
Then we learned how to roll money forward into the future with compounding and future value, watching out for those frequency traps.
And we pulled money backwards with discounting and present value, stripping out the phantom growth.
We tackled multiple cash flows, the difference between an ordinary annuity and an annuity due.
And finally, we used those mechanics to evaluate real corporate projects and calculate loan payments with amortization.
It's a complete framework.
It really is. But before we sign off, there's one final kind of mind-bending concept from the key terms section that we haven't touched on.
The perpetuity.
Yes, a perpetual annuity.
Yeah.
Because we've been dealing with finite timelines, 5 years, 10 years. What happens when a cash flow lasts forever?
It stretches to infinity. And human logic says, well, if I get paid forever, the value today must be infinite, right?
It seems impossible to calculate.
But because of the magic of discounting, an infinite stream actually has a finite value today.
Wait, really? How does that work?
Because the further out into the future a cash flow is, the more aggressively it gets shrunk by the discount rate. Cash flows hundreds of years from now are basically discounted to zero in today's terms.
Wow. So the math actually catches up to infinity.
It tames infinity. It's a beautiful thought experiment. I'd encourage the listener to ponder how the formulas we just learned might adapt to an infinite timeline. It's a great way to test your TVM intuition.
It really is. Well, you've got the framework now. You know how the time machine works. We want to wish you the absolute best of luck on your MBA exams. Thanks for joining us on this deep dive into the source material. Catch you next time.